Auzubillahi minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. In the last lecture, we have studied about the differential equation having first degree and first order and nth degree, in which we have studied the several cases. In the last lecture, we have studied three cases. Now, fourth case we are going to study today, which is Clairaut's equation. It is a special form of equation solvable for y. This equation is of the form y is equal to px plus fp, function of p, equation number 1. Its general solution is obtained simply by replacing p by c, such as examples. Solve the following differential equation. P is equal to log px minus y, where p is equal to dy by dx. The given equation can be written as y is equal to px minus e to the power p, which is of Clairaut's form. Therefore, its solution is y is equal to cx minus e to the power c, where c is arbitrary constants. Now, we are going to study about the next method, orthogonal trajectory. The procedure to find the orthogonal trajectories of the family of curves f x y c is equal to 0, equation number 1. Form the differential equation in the form f x y dy by dx is equal to 0, equation number 2. Now second, in equation 2, replace dy by dx by minus dx over dy, so that the product of their slopes at each point of intersection is minus 1. And then find the solution of the differential equation of the orthogonal trajectories f xy minus dx over dy is equal to 0. For example, if the streamline paths of fluid particles of a fluid flow near a corner are the rectangular hyperbola xy is equal to c, where c is constant, find the orthogonal trajectories called equipotential lines. Solution: it is given that xy is equal to c, which is equation number 1. Now differentiating with respect to x, we get x dy by dx plus y is equal to 0. Replacing dy by dx by minus of dx over dy, we get minus of x dx over dy plus y is equal to 0, or x dx minus y dy is equal to 0 is the differential equation of the orthogonal trajectory, whose solution is, which again represents a rectangular hyperbola and is required orthogonal trajectories. So finally its solution will be x square minus y square is equal to c. Now we are going to study the next topic, ordinary differential equations of higher order with constant coefficients. The general form of such an equation is dn y over dxn plus a1 dn minus 1 y over dxn minus 1 plus a2 dn minus 2 y over dxn minus 2 plus up to an y is equal to capital X. Equation number 1. Using the differential operator capital D for d over dx small d over dx, then equation 1 can be written as, within the bracket, d capital D n plus a1 d n minus 1 plus a2 d n minus 2 plus up to an bracket close y is equal to capital X, equation number 2, where capital X is the function of the independent variable x and ai are constants, where I is equal to 1 to n, or fd into y is equal to capital X. Solution of the equation 2 will be done in two parts, as first part ft into y is equal to 0, equation number 3. The solution of equation 3 is known as complementary function. Complementary function. And second, y is equal to capital X over ft, function of d, equation number 4. The solution of the equation 4 is known as particular integral, pi. Thus the complete solution of the equation 1 is y is equal to complementary function plus particular integral. Now we are going to find the complementary function for the given differential equation. From equation 3 we get d minus m1, d minus m2, d minus m3 up to d minus mn into y is equal to 0, where m1, m2 up to mn are the roots of the auxiliary equation a e fm is equal to 0, or mn plus a1 mn minus 1 plus up to an is equal to 0, equation number 5. The roots of the auxiliary equation are all real and distinct. Therefore, the solution corresponding to dm minus 1, dm minus 2 up to dm minus n, d minus mn y is equal to 0 are y is equal to c1 e to the power m1x plus c2 e to the power m2x plus up to cn m e to the power mnx, where c1, c2 up to cn are arbitrary constants. Now case 2, the auxiliary equation having multiple roots. Suppose m2 is equal to m1. The solution of equation of 3 is y is equal to c1 plus c2x e to the power m1x plus c3 e to the power m3x plus up to cn e to the power mnx. Similarly, if m1 is a three-fold root, that is m1 is equal to m2 is equal to m3, then the corresponding part is in the solution is c1 x square plus c2x plus c3 e to the power m1x. Case 3, auxiliary equation having complex roots. The solution can be written as y is equal to e to the power alpha x, c1 cosine beta x plus c2 sine beta x. Particular integral. Particular integral is depending on the form of capital X. So we are going to write the formula for taking different form of capital X. First, when a capital X is equal to e to the power ax, therefore particular integral will be 1 by fd e to the power ax is equal to 1 by f. D is replaced by a, so f a e to the power ax, provided f of a is not equal to 0. Now second one, when capital X is equal to sine of ax plus b or cosine of ax plus b, implies particular integral is 1 by f d square sine ax plus b over cosine is equal to 1 by f minus of a square sine ax plus b cosine ax plus b, provided f of minus of a square is not equal to 0. Now third one, when x is equal to sine hyperbolic ax plus b or cosine hyperbolic ax plus b, then 1 by f d square is sine hyperbolic ax plus b cosine hyperbolic ax plus b is equal to 1 by f of a square sine hyperbolic ax plus b cosine hyperbolic ax plus b, provided f of a square is not equal to 0. Now fourth one, when x is equal to x to the power m. If capital X is a polynomial in x, then 1 by f d x to the power m is equal to ft inverse x to the power m. Fifth one, when a capital X is equal to e to the power x dot v multiplied, where v is any function of x. Hence 1 by f capital D capital X is equal to e to the power x 1 by f d plus a v. Now we are going to solve the problem. First problem is solve d cube plus 2d square minus 5d minus 6 into y is equal to e to the power 4x. The given equation can be written as capital D plus 1, capital D minus 2, capital D plus 3 into y is equal to e to the power 4x. The auxiliary equation has the roots minus 1, 2, 3 minus. Therefore, complementary function is equal to c1 e to the power minus of x plus c2 e to the power 2x plus c3 e to the power minus of 3x. Therefore, particular integral pi is equal to 1 by d cube plus 2d square minus 5d minus 6 e to the power 4x is equal to 1 by 4 cube plus 2 into 4 square minus 5 into 4 minus 6 e to the power 4x is equal to 1 by 70 e to the power 4x. The complete solution is y is equal to complementary function plus particular integral, which is equal to c1 e to the power minus of x plus c2 e to the power 2x plus c3 e to the power minus of 3x plus 1 by 70 e to the power 4x. Another question, solve d square plus d plus 1 into y is equal to sine 2x. The equation is d square plus d plus 1 into y is equal to sine 2x. The roots of the auxiliary equation are minus plus minus I root 3 by 2. Therefore, the complementary function is e to the power minus a half x c1 cosine root 3 by 2x plus c2 sine root 3 by x 2x, and particular integral is equal to 1 by d square plus d plus 1 sine 2x. This is equal to 1 by minus of 4 plus d plus 1 sine 2x. Now multiplying numerator and denominator by d plus 3, d minus 3, d plus 3. So d plus 3, d square minus 9. So d plus 3 minus 4 minus 9 minus 1 by 13, 2 cosine 2x plus 3 sine 2x. And thus the complete solution is y is equal to complementary function plus particular integral. Now we are going to solve another problem. d3y over dx cube plus 5 dy by dx is equal to sine hyperbolic 2x. The equation is d square plus 5 sine hyperbolic 2x. The auxiliary equation m square plus 5 is equal to 0 has roots. So m is equal to 0 and m is equal to plus minus I root 5. Therefore, complementary function c1 plus c2 cosine root 5x plus c3 sine root 5x and particular integral is equal to 1 by d square plus 5 sine hyperbolic 2x. This is equal to 1 by 9d sine hyperbolic 2x 1 by 9 integration sine hyperbolic 2x dx is equal to 1 by 18 cosine hyperbolic 2x, and thus the complete solution is y is equal to complementary function plus particular integral is equal to c1 plus c2 cosine root 5x plus c3 sine root 5x plus 1 by 18 cosine hyperbolic 2x. The another problem, d3y over dx cube plus 2 d2y over dx2 plus dy by dx is equal to minus e to the power 2 x plus x square plus x. The given equation is d3 plus 2d square plus d into y is equal to e to the power 2x plus x square plus x. For complementary function, the auxiliary equation is m cube plus 2m square plus m is equal to 0, whose roots are m is equal to 0, minus 1, minus 1. Hence, complementary function is c1 plus c2 plus c3x e to the power minus of x. And particular integral is equal to 1 by d cube plus 2d square plus d e to the power 2x plus x square plus x. So this will come outside 1 by 2 cube plus 2 square plus 2 e to the power 2x plus 1 by d cube plus 2d square plus d x square plus x. And for integrating for this part, we use the binomial method to expanding this function. So which is 1 by 18 e to the power 2x plus 1 by d 1 minus 2d plus minus 2 minus 3 over 2 e t square x square plus x. So 1 by 18 e to the power 2x plus x cube by 3 minus 3x square by 2 plus 4x plus 3. And therefore the complete solution is y is equal to c1 y is equal to c1 plus c2 plus c3x e to the power minus of x plus 1 by 18 e to the power 2x plus x cube by 3 minus 3x square by 2 plus 4x plus 3, or y is equal to c1 dash plus c2 plus c3x e to the power minus of x plus 1 by 18 e to the power 2x plus 1 plus x cube by 3 minus 3x square by 2x plus 4x, which is the required solution of the given differential equation.